of a generator. So here we can see many parts. One is a frame or a yoke. Then we have as a pole shoes, field winding, armature, commutator, interpoles, shaft, a commutator segment. Like that we have a many part. Now the first part will be the yoke. So this is the actual DC generator. You can see it will consist of all the parts. Now we'll take a part by part. The outer frame. So first we will take with the yoke. So it is the outer frame of a machine, which is made up of a cast iron or cast steel, and it acts as a supporting frame for the machine, and it will have a different things will be connected to this. One is a feet, so where a machine will be kept on the place where it is to be mounted, and it will be bolted so that the machine will not move during the running condition. Then the outer frame, then we have a terminal box and the lifting eye. So since the machine is with a very weight of the machine is very high, they will provide with a lifting eye whenever they want to pick the machine, so they can take help of the lifting eye. So you have a yoke which will act as a protecting shield for the generator, and it will provide a mechanical support for the poles. So for the small generators, the yokes will be made up of a cast iron. For the larger generators, yokes will be made up of a cast steel. So next one will be the pole core or the pole shoes. So here you can observe here. So this entire thing is a pole core, and this is a pole shoes. So you can see a laminations here, a laminated pole core. So you can observe here, this is the pole what we have. So it consists of a pole core and the pole shoes, and it is basically spread out the flux in the air gap. The poles are usually fixed inside the yoke. So this is the yoke part what we have. Inside the yoke, the poles will be, of course, will be fixed by using a bolts. The cross section of the pole core is in the rectangular shape. You can see this is in the rectangle shape. By attaching a pole shoe at the end, which will have a cylindrical surface. This is the pole shoe which will have a cylindrical surface. Usually pole cores are made up of steel laminations and insulated from each other. You can see a steel laminations, it's combined together, and in between two steel laminations they will have a insulations. Then what is the function of a pole shoe? So to support a field coil and to increase the area of the magnetic field. So this is the function of a pole shoes. Then next one will be the pole coils, or we can also call them as the field coils. The field coils are wound on the pole core and are supported by the pole shoes. You can see this is the pole core. Above that you can see this is the coil. They consist of a copper wire wound by the former. The current passing through the pole coils will produce the necessary flux. So that's why the field coils are important. Then next one will have is a armature, which is a rotor part. So armature, you can see it will be in the cylindrical shape. The armature core will be in the form of a cylindrical shape, and the outer periphery is made up of steel laminations to reduce the eddy current loss. You can see this is made up of a steel laminations. The winding inside that will be of two types. One will be the lap winding, and another will be the wave winding. So wave winding will be something like this. So you can see it's in the form of a wave. You can see at the sea, right? So that's why it's the name is called as a wave winding. If you consider with the lap winding, so one or the other it will be placed, so it's overlapping over the other. That's why the name is called a lap winding. So the two different types of winding which will be placed on the armature will be a lap winding and the wave winding. So you can observe the lap winding here. So on the commutator segment it will be placed one over the other, it is overlapped, so it is called as a lap winding. Here in this case the number of parallel paths will be equal to the number of poles. So the number of parallel paths will be equal to number of poles. So if A will be equal to P, where the number of parallel paths will be equal to number of poles. A represents the number of parallel paths and P represents the number of poles. If you consider with the wave winding, you can see it's in the form of a wave. So here the number of parallel paths, A value will be equal to 2 in case of a wave winding. And your wave winding is suitable for high voltage and low current machines like a generator, which will be used for the lighting. But the lap winding will be suitable for high current and the low voltage machines like welding plants. Next one will be the commutator. So above the rotor, you can see this is a rotor. Above the rotor we have is a commutator. So why we require a commutator? Because whenever a magnetic flux will, whenever the rotor rotates, right? So the field coil, whenever we pass through the current through the field coil, a magnetic flux will be created. So here the rotor will be rotating, which will be cutting the flux. Because of that, the EMF will be induced. So whatever the EMF will be induced, it will be a AC. So that's why we require a commutator, which is used to convert a induced AC in the armature to a unidirectional current, and it is made up of a wedge-shaped hard drawn copper, and the segments are insulated with a thin layers of a mica sheets, so which will convert a AC current into a unidirectional current. You can observe the waveform here. So that's why it is used to convert from a AC current to a unidirectional current. That is the use of a commutator. Then above the commutator the brushes will be placed. So whatever the current which is converted from AC to DC on the commutator, it has to be collected. That's why on the commutator our brushes will be mounted. Usually the brushes will be made up of a carbon or the graphite, and it will be usually in the shape of a rectangular block. So the number of brushes usually depends on the magnitude of the current which has to be collected from the commutator. Then we have a bearing. So usually for the free movement of the rotor and the coils, so we'll be using with the bearings. So it is similar to in the cycles or the motor vehicles what we will be using for the rotation of the wheels. So this is the actual DC generator. You can observe here, right? This is a cross-sectional view of that. This is a side view. So, and this is how the schematic diagram is. What all the things we have discussed is, one is a yoke outer part. Inside that we'll be having a pole core. Above the pole core, field coils will be mounted, and on the shaft, this is a shaft. On the shaft, the armature core is there. Above that, the windings will be placed. There is a armature winding. Between the armature core, a commutator will be connected, which will be converting a AC current into a unidirectional current. And for the smooth movement, we'll have a bearing. Above the commutator, brushes will be placed to collect the current. So this is how the construction of your DC generator is. So now we can see how it will be mounted one by one. This is the outer frame yoke. So it's the outer part, as we discussed, it's the only the outer part, and it will act as a support, a mechanical support. On the yoke, a poles will be mounted. So it will contain a pole core and a pole shoes. A pole core will be in the form of a rectangular shape, and pole shoes will be in the form of, it will be connected to the pole core, it will be in the form of a cylindrical shape. So usually whatever the pole core or the pole shoes we are going to use, it will be in terms of a even number. Next, here we can see this is a shaft. Then on the shaft we can observe the rotor armature, which will be placed, and on the pole the field windings will be placed. So on the pole the field windings will be placed. Then inside the rotor will have a commutator, so that whatever the EMF will be induced, AC EMF will be induced to it, has to be converted to a DC. In the next diagram you can observe on the commutator the brushes are placed to collect the current. Then from the brushes it will be connected to the terminal box, where we'll be getting the supply. So whenever we will give the supply to the field winding, which is mounted on the armature, which is mounted on the pole shoes, right? So a magnetic field will be created. You can observe here the north pole and the south pole. So electromagnetic, because of the electromagnet, we will have a temporary magnet, electric field will be created. So here we have a shaft, on that the armature will be mounted. So when the armature rotates, we know that whenever we have a magnetic field inside that conductor rotates, EMF will be induced. Or if we keep the plate constant or the conductor constant and the magnetic field will be rotating, the EMF will be induced in both the cases. In this case the field is kept constant and the armature, the plate, is rotating. So obviously it will cut the flux and the EMF will be induced. So whatever the EMF will be induced, it will be AC EMF will be induced. Using a commutator it will be converted to DC. Above that the brushes will be mounted, which will collect the DC current and it will be given to the terminal box. So this is how the DC machine will work.